Um, this last section deals with something known as reaction mechanisms. It's how reactions take place. It's the reason we determine rate constants and study reactions, as we want to, as scientists, understand how reactions happen. So we already looked at one earlier. That's the reaction we're looking at on the left here. And in this reaction, if you remember right, what we had was we had fluoride, fluoride plus chloroform. That's the name of that again. And then that makes chloroform. I wrote chloroform. I was like, what's happening here? Fluoride, and then that gives you chloroform, CH3F, plus Cl minus, like that. Okay, so that's how that reaction takes place. The fluorine, remember, comes in. We can watch the video.
A bimolecular SN2 mechanism for a nucleophilic substitution reaction. The formation of the bond between the carbon atom and the entering species occurs simultaneously with dissociation of the bond between the carbon and leaving group.
So the idea is that all happens in one step. Okay, so we call that a one-step reaction. And in mechanisms, reactions, we've referred to them happening in steps. So we write a step each time a bond is broken or formed, right? And so this is the step for this reaction. So what I want to show you next is actually on the next slide, because I want to write it out. It takes a little bit more time. Unfortunately, the video is going to play, but we'll skip it and we'll get to it.
In the bimolecular...
There you go. So this is the new reaction, okay? So what we're going to write is what happens in each step. Now, I have H plus and Cl minus both present, right? But that's actually HCl. Right? So in my reaction, what I have on my reactant side is I have C, and I'm going to show you how to write this abbreviated, CH3, because that's all of this, okay? Carbon with those guys. And then I have OH on there, plus H, and I'm going to just do the plus for now so that you can see how this works out, okay? So let's watch the video for a little bit. I'll erase it so it's not covering, and hopefully you can hear it okay.
A unimolecular SN1 mechanism for a nucleophilic substitution reaction, the bond between the carbon and the leaving group.
So you notice what happened, right? You formed this. And you can scrub back in the video. If I do it, it'll break. This program doesn't work that great, but I can scrub back and show you. But that's what you formed during the course of this reaction. Now, the reaction's not done yet, okay? So let's then write this. The next thing that happens, so remember, every time you break a bond or make a bond, the next thing that happened is you broke a bond. The bond that you broke was between actually the carbon and this oxygen, okay? So that's actually another step. So I have CH3, I'm sorry, CCH3. And then OH like this. There's a positive sign here. I don't know if you noticed, the electrons in the bond went to the oxygen, and you ended up with this. Because that gives you water. So you get water, but you notice here you get this positive charge. So that's where we are in the video right now, okay? And then we can continue on, and we can watch what happens next, or not.
Breaks prior to formation of the bond between the carbon and the entering group.
So that's another step in the reaction. So I have my carbocation, this is a carbocation. I don't know why I keep doing this to myself. I always can't write two carbons in a row, it turns out. and this forms chloroform. That's or not chloroform. It forms a, I guess, T-butyl chloride is what it's called. But you don't need to know the name. It just gives me something to talk about. So T-butyl chloride. Okay, so interesting things are happening here to me anyways. And you don't actually have to be able to like watch a video and write it, but I want you to see it because you're going to have to think it very soon in organic chemistry. Like this is how reactions take place, okay? This helps us understand different factors which affect the rates of chemical reactions. But overall, what I have in this reaction, notice this is not a product or a reactant. Neither is this a product or a reactant, because they get formed during the reaction, but actually the overall process is simply CH3OH plus HCl. That, remember I was telling you how this and this come from HCl, makes CH3,3Cl plus H2O. And this is also a type of substitution reaction where I've taken the OH and substituted it with the Cl. That's all you really kind of see that's going on. This is my overall reaction. Now, it turns out, like, if you take each one of these steps, so this is a 3-step reaction mechanism, right? And you add them all together, what you'll find out, these things that are here and disappear, right? That's what actually doesn't end up in the end. These are known as intermediates. So, like if you ever, when you were a kid, I was going to say if you were ever a kid, but I know you were all kids at one point. If you were a kid and you made a Lego set that was really big, right, and you had this final thing that you were trying to make, oftentimes you built little pieces and stuck those together in order to make the final Lego set. Those little pieces, which aren't part of the final product, are the intermediates of your project. And so just like you have intermediates in your work or in your travels or in preparing food, right? You don't eat raw eggs, for example. You don't. There's a lot of things. Sometimes those things are intermediates in the reaction.
In the unimolecular.
So, sorry, this animation is not supposed to be there anymore. So I have an overall reaction, right? And it's broken into what are called steps or elementary steps, the technical term for these things. Each step has its own associated rate constant, right? Each one has a K value. When you add the elementary reactions to get the overall reactions, the stuff that doesn't show up in the final reaction are known as intermediates. Okay, so this in this case that gets made and used up. Oh, my pen stopped working. It's made and used up during the course of the reaction. Those are known as intermediates. So this is that same reaction sort of summarized. I have a reaction that's broken up into elementary steps. Oh, the lights went off. I gotta go like this to make the lights go on. Sometimes I have to stand up. There we go. I'm not gonna edit that out. It's a pain. I have, in this case, it says the second step is the rate determining step. So that's the slowest step in the reaction, okay? And it determines the reaction rate. So the reaction rate is always determined by the slowest step. So think about why that is, right? This is a series of 2 reactions that is taking place. If the first step was slow and the second step was fast, the second step's just waiting for the first step reaction to give it, right, the intermediates in order to continue on. On the other hand, and so the first step would determine how fast the reaction goes overall. But what if the second step was the slow step, right? If the second step is the slow step, then the first reaction is going really fast. The intermediates will build up, but they can't go through the reaction any faster than the second reaction allows it to. So the reaction rate is always determined by the slow step, okay? Now, as it turns out, and this is what we're going to be doing next, is you can use the slow step to figure out what the rate law for the reaction will look like. So let me say that again. The slow step of the reaction, the rate determining step, or RDS, is what we use to write the equation for the rate law. So to derive the rate law, what I decided I'd do is I just show you one mechanism without a lot of chemical compounds, just A's and B's, and show you how you would derive the rate law from these reactions. But you do exactly the same process with any chemical reaction when you're given the mechanism. Okay. So there's three cases. One, overall reaction is the only elementary step. Then you can write a rate law from it very easily, and I'll show you how to do that. Or the rate law is a multi-step, right, reaction. But the first step is rate determining. That one's super easy too. We only ever do two and maybe a three-step mechanism. Most likely the most you'll see in this class for now is two steps. If it's a two-step mechanism and the second step is the slow step, that's the one that requires some algebra, and I'll show you how to do that. Okay. So let's do the simplest cases actually, or cases 1 and 2. So let's see, yeah, case 1, right? The overall reaction is the only elementary step. Then all you do is you say rate, right, is equal to K times A times B. Now this K is actually known as a microscopic rate constant because it's for a step in a reaction mechanism. But since it's the only step, it is actually the intrinsic rate constant you've calculated before. Okay, it ends up being the same thing. So if the reaction looked like this one, right, which is pretty rare, okay, I'll talk about that in a second. And there's a whole slide that I skipped that talks about why it's rare and stuff, but I just thought I wanted to get to this part. If you have 2A plus B is equal to C plus D, right, and it's a one-step mechanism, then it turns out you would write it just like this. And the 2, right, is the coefficient right there. So that's for single-step reaction. So let me ask you to think about this, right? Bimolecular reactions and unimolecular reactions are fairly common. In a unimolecular reaction, a molecule has to have enough energy, and maybe it's a decomposition, for example, to decompose, a bond breaks. For a bimolecular reaction, two molecules collide, right, with the orientation and the energy necessary for the reaction to take place. Now, a termolecular reaction, that is the term we use for more than two, okay, atoms or molecules coming together in the step in an elementary step, are very rare because what happens is three molecules have to get together at the right time, at the right orientation. So that's collide, right? At the correct orientation and have the correct energy. It's kind of like scheduling a meeting, like we're all Zooming right now, right? And you want to meet with somebody on Zoom. That's actually relatively easy, office hour kind of thing. Oh, you want to meet on Zoom? Sure, let's meet on Zoom. And then you meet, right? I've already had the situation where two people wanted to meet at Zoom. And so I'm saying, well, can you meet at this time? They're like, no, I can't meet at that time because I have a Zoom session with somebody else. And then the other person says, oh, well, that's the only time I can meet today. Can we meet tomorrow at this time? Right? And then it just goes on and on and on until you finally can have a meeting with all three of you there at the same time. So the probability of more than two molecules actually coming together with all the other factors that are involved is actually relatively rare. There's only a small handful instead of millions of reactions that are termolecular versus bimolecular. Okay, so that's for a single step reaction. Now, it's also true, okay, if it's a multi-step reaction, but the first step is really slow. So what I've done is I put in different rate constants in for each step of the reaction. So I have a 2A plus D goes to C plus E, and I've sort of made up a mechanism for it. I said 2A's have to get together, that makes B and C, and then B gets together with D, and that makes E, right? And so this is the first step of the mechanism. This is the second step of the mechanism. My intermediates, for example, would be, I guess, B, because everything else shows up in the reaction. Yeah, everything else shows up in the reaction. So if the first step is the slow step, right, then the second step's rate doesn't matter. And the analogy I use in my type notes, and I often use in class when I draw, is two funnels, and I pour water in B. Does it matter, right, how big the second funnel is, as long as it's bigger than the first? Not really, because the water is going to go into B, right, and then just fall through. Sorry, this is not B. This is actually a panel B from an image. But it's going to fall through this funnel, right, and just go fall through this one as well. Now, if you reverse the funnels, right, if you took, I think that's actually what I did in the next one, or I guess I didn't show it. If you make the second step the slow step, right, and you switch those funnels, then water can go through the first one, but then it hits the second one and it stops, right? Because the second one is smaller and doesn't let it through the second funnel, okay? So if it's the first step is the rate determining step, right, then the rate law comes from just the first step. And that's going to be, right, this. A has to run into A. That's actually what that means. Two A's have to get together, and then the rate constant determines how fast that, how much of that's going to go on to form a product, or an intermediate in this case. So the rate law becomes K times A squared. The reaction would be zero order in D, because D comes in after the rate determining step. So its concentration doesn't matter, because that reaction itself is so much faster than the first reaction, okay? All right, so let's cover the third case. And then I actually, in my notes, in my type notes as well, I have a case that involves chemical compounds, and I work it out in those notes as well. So this is actually the following slides, but you can read through that in the handout if you want to do that, or you can just read it on the slides and work it out from the slides. Okay, so this is a case where the second step is the rate determining step. So that means this step, okay, K2, this step here is the slow step. So K2 is smaller than K1. That's what we mean. It's slow. We can still write a rate law from that. So we would write rate equals to, right, concentration of B times the concentration of D. Right, and then we'd have to throw in K2. That's the microscopic rate constant for the second step. So that would be the rate law, except there's one problem with it. And the problem is that B is an intermediate. And if you remember how we use these rate laws, we use them with concentrations of reactants to figure out like how fast the reaction is going, right? So if it's not a reactant or a product, for example, you can't control its concentration, right? And as a result, it's not useful. So what we need to do is figure out how to rewrite this equation so that it doesn't have B in it, the intermediate. And this is how we do this. We assume, okay, that this first reaction goes to equilibrium. In other words, the way we would like to say it is the concentration of B builds up high enough that there's now a reverse reaction taking place. It's going backwards as well as forwards. So we introduced this idea of reversibility before, but I have a K minus 1 now for going in the backwards direction. Now, the forward reaction rate is going to be equal to this. A times A, right? That's K1. And that's going to be how fast it's going in the forward direction. In the reverse direction, so this is forward, the reaction is going to be equal to K minus 1, so this is the reverse, times B, right? B times C. I'm just going to use letters like that. So there's a forward rate of reaction, there's a reverse rate of reaction. When the reverse rate builds up to be fast enough, okay, what's going to happen is the forward and reverse will become equal to each other. In other words, these two at equilibrium, right, will be the same. This means I can solve this equation for B by dividing both sides by K minus 1 and C. And that gives me B is equal to K1 over K minus 1. I just separated them out because I like them together, times A squared, because it's A times A divided by C. And you notice C is a product and A is a reactant. So now what I can do is substitute this in, okay, to here. And when I do that, I will have rate, or reaction rate, right, is equal to K2 times K1 divided by K minus 1 times A squared times D over C. Now, that's a relatively complicated rate law because I just made up a reaction. But that would be the rate law for the reaction. Now, one other thing to say is I have this set of rate constants. That's a collection of all the microscopic constants, the ones for the steps of the reaction. That's what you see, right? But the actual thing that you would test in a rate law, for example, would just be a K. So that's the intrinsic rate constant. That's what we measured before, but it's actually a collection of microscopic rate constants in the mechanism. So this will be A squared times D over C. This is an okay, even though it looks weird, it's an okay rate law because it only has reactants and products in, things we can manipulate to see if the mechanism is correct. So one of the things that's interesting about this particular mechanism, it tells me if I start with some product in the reaction will actually go slower. So you can actually test that in the reaction, okay? So that's how you determine, right, a rate law from a mechanism if the second step is the slow step.